quick point. We're starting from slide 3, so that's where you might want to move to. Yeah, are we ready? The Great Barrier Reef, a miracle of nature. It attracts thousands of tourists because of its national natural beauty. But more often than not, tourists are finding plastic in the sea that is harmful not only for the marine life, but for all life. It is estimated that by 2050, there will be more plastic in the sea than there are fish. Where is this plastic coming from, and why is it ending up in the sea? The United Nations estimates that only about 9% of all the plastic produced in the last 60 years has been recycled. Only 9%. There is now an increasing effort to solve this problem, including that by the Australian government. This is reflected in their national waste policy, which is an ambitious approach, and we want to highlight some of its key aspects. Currently, Australia is exporting a lot of its waste to foreign countries such as Asia, but the Asian countries like China are now introducing bans on imported waste. And the Australian government is now forced to set targets to stop the export of plastic waste altogether. However, what do we do with the plastic that will stay in Australia? In Queensland itself, most of the waste is sent to landfill or incineration. But even these are reaching capacity, and current recycling solutions are already struggling, especially with the stop and introduction of this ban on export of waste. The system is near collapse, and we need solutions. To put things into perspective, currently in Queensland, the recycling rate for your municipal waste is 27% only. And the government waste policy has set the ambitious target to raise the resource recovery rate to 80% in the next 10 years. How is that going to happen, and who is going to do that? How can we recycle the waste? Well, there are 3 ways of doing so. Firstly, this is what you would traditionally think of recycling, which is when you shred, melt, and reuse the plastic. This is shown on the left and is called mechanical recycling. You can only do this with the high quality plastics. Secondly, you can use what's called thermal recycling, where a lot of the waste actually ends up because it's mixed with food waste, or it might be of poor quality. And this process generates a lot of greenhouse gases and a lot of toxins. But there is a third way, the way of chemically restructuring the material. This type of recycling is called chemical recycling. This takes the most difficult to recycle plastics and turns them into new material that can be reused and put back into the economy. This operates on a much smaller scale than the other type of recycling. What are you doing?
I'm sharing screen. We share our screen.
We should be sharing screen.
We're not seeing the screen. I haven't seen your presentation.
There we go.
Are you seeing the screen now?
Yes, yes.
Yeah, I thought they were down.
Good work. No problem.
Okay. Speaking beautifully. But then
Okay. Anyway. Okay. I'll have to charm you with my words then. Okay. Now, I was just talking about chemical recycling. I'll pick up from there. Chemical recycling. I was saying it takes the most difficult to recycle plastics and it turns them into new materials. These can be then reused and inserted back into the economy. It operates on a much smaller scale than the other types of recycling, which means that you can recycle more locally where the waste is coming from. It is no surprise then that the Australian billionaire Andrew Forrest says that current solutions for recycling plastics are not going to solve the plastic crisis. This is why he has pledged $300 million towards chemical recycling efforts. Why is he saying that current recycling methods are failing? Well, there are 3 reasons for this. The first one is that these require a lot of investment and are extremely expensive to run. Secondly, they require a lot of greenhouse gas emissions and toxins to the environment. And thirdly, they struggle to recycle mixed or deteriorated plastic waste. This is where Plastalyst comes in. Our patented catalyst turns the most difficult to recycle plastics and turns them into new material, truly creating a circular economy. If you obtain one of our machines for Queensland, you can convert 24 tons of waste a day into 14 tons of pure carbon. We will provide you with the catalyst to do so. And having looked at the expenses of processing this much waste in Queensland, we see that the payback is as little as 5 years. Robert, I'd like to ask you, what differentiates Plastalyst from the other waste solutions existing out there?
Firstly, our small machines can recycle waste much cheaper and use a lot smaller investments. Compared to this pyrolysis, we only require 1/10 of the investment and run on half the costs. Whereas traditional recycling requires large infrastructure. We are offering smaller scale recycling, which is cheaper and can be deployed locally where the waste is produced. Regarding the second problem Hassan mentioned about the emissions, our process produces no greenhouse gases and runs on low temperatures, which require very little energy. Compared to composting, Plastalyst can produce and process waste 240 times faster. 240 times. And lastly, we can process the most difficult to recycle materials, such as mixed waste, deteriorated plastic, multi-layered plastic, which makes this process truly scalable. Plastalyst is addressing the 3 recycling problems and produces pure carbon. The carbon generated from our process can be used in many different ways. Importantly, we see this as an opportunity for Queensland to reach their goal they've stated of becoming the Asia-Pacific biohub of the future. There are 3 stages to our project. The first is a proof of concept with our small machine. Then we'll go to a larger pilot with a larger volume machine that can produce larger volumes of waste. And lastly, a large-scale commercialization, which you can roll out on the national level. The proof of concept we want to do for several reasons. Our advantage is that we've already done proof of concepts before in Japan with food waste management companies. Waste over has only ever been up to 10% of the waste content. So there's only ever been 10% plastic in the waste content. This proof of concept in Australia will be our first field test to prove that we can do much higher quantities of plastic in the waste. which so far we've only done in the lab. We can also measure the emissions, which is very important to gain the trust of investors for our next stage. A risk we have identified is PVC, which contains chloride, and it damages our machines. We will manage this risk by adding the right amount of alkali to neutralize this chloride. We believe we can do this in less than 12 months because we have done it before. For example, this is carbon data from one of our previous proofs of concept, where you can see the carbon generated is 99.5% pure. We received feedback from the first round of this competition. There was no information on how the catalyst is produced and how much greenhouse gas emissions are coming from that. And currently, we have an early way of producing it, which does produce some CO2 emissions. And we want to make and paint a picture there for you how much CO2 emissions this is producing. So consider the elephant in the room. Hassan, what is that?
Incineration. It produces 450 kilograms of CO2 per ton of waste.
In comparison, our catalyst is a mouse and produces as little as 0.05 kilograms of CO2 emissions. And this is only the early stage. We are further developing our catalyst to be recyclable, reusable, so that this mouse becomes an ant. Have a look at our machine. Here is our pilot test in Japan, and you can see the whole machine is small enough to fit in a room, so it can be placed wherever the waste may occur. And you see this is a continuous process machine where the waste is input at the back of the room at the far end, and it's processed through the rotating barrel constantly, and on the other side the carbon is coming out. You can also see the extractor fan here for the non-toxic gases that are released and the vapor that's coming out of the process. And this is constantly producing carbon here. There, the carbon is coming out of the end of the machine, going onto the little conveyor belt that's in this box, transported up, and there it is. Pure carbon. You can put your hand out and it's a nice feeling. To break down the costs of the first phase, the proof of concept, most of it is going to the machine, and in total we require around 250,000 Australian dollars. And we believe we can install the machine within a few weeks because it's ready to ship from Japan. Most importantly at this stage is showing the low emissions, because this will allow us to go to a larger stage and get investment. This larger stage, the pilot phase, will bring a machine to Australia that is 24 times as big and process a lot more waste. The purpose of this pilot is to see how the machine performs at scale. At this stage, we're testing that we can make sure there is a constant supply of catalyst, and ideally we can produce it locally. We're testing how we can train staff locally, and also how we can guarantee a constant offtake of the carbon in Australia. Lastly, important for investors, again, assuring that even at this larger stage, there are no greenhouse gas emissions or toxins being released. There is a risk we have identified, which is that more complex polymer chains require longer processing times, and at scale, that can slow down the process. We will mitigate this risk using a shredder. Also, we're developing zeolite as a new catalyst, which is way more powerful, meaning that the process is sped up considerably. We require for this pilot phase 420,000 Australian dollars. mainly to pay for the large machine. After that, the large machine has proven that we can do this on scale, and more of these machines can be deployed all over Australia. Our business model is to sell our machines with a subscription to municipalities, waste management companies, islands, agricultural operators, and organizations that process plastic waste with a subscription on the Catalyst. This is our early stage business model, because though the upfront cost of the machines is a real inhibitor for many organizations. For later stages, in a couple of years, we are considering public-private partnerships. The reason for that is that they are partially owned by private investors and also partially by banks. And that helps to guarantee a constant supply of waste on one side and a constant offtake of the carbon from the other side. So why would the government invest? And why would private investors invest? For the government, this is a much cheaper way than to solve their waste problem that we heard about earlier. They can leverage private investor funding rather than investing in recycling facilities themselves. Private investors see this as an opportunity of a quicker payback time for industry standard. And this is attractive. This is attractive to Shell Venture, who are a large producer of plastic and petrochemicals, and they have a strong green agenda, because Shell wants to reduce their greenhouse gases by 50% in the next 30 years. If they invest in us, we can help them to achieve this goal. This fast payback is one benefit of our efficiency. Secondly, there's also the small-scale nature of our recycling. That means that we can produce and process the waste locally into carbon, and this is a lot more effective than current centralized solutions, because it means the waste doesn't have to be transported over distances, especially in large countries. This also creates jobs locally, because we will train those technical operators. Research shows that sending the waste to recycling centers rather than to landfill creates 3 times as many jobs for Australia. And lastly, we are contributing to the targets of the national waste policy mentioned in the beginning. We started with the plastic crisis, you can see on the left. Then we talked you through our solution, you can see on the right. And then we explained the tangible benefit to Queensland and Australia, which you can see in the middle. Tadashi, how about us? How about our team? Thank you.
So we are well balanced between the business, finance, and engineers. So we have 2 engineers and more, as well as I myself used to do project financing, including in Australia, in Asia for infrastructure and renewable energy projects. And we have strong mentors on material science, and also Stephen on industrial sustainability that we have. Next slide. The market is growing, so not only for food waste and plastic waste industry, lots of companies are now focusing on how to solve the plastic, ocean plastic waste. And for example, Nike, Adidas, these retail companies using ocean plastic waste as, for example, recycling shoes and watches, just to raise awareness and for branding purposes that we want to target on. We have attraction, so we have already sold two food companies in Japan successfully, and we already carbonized in our laboratory for the ocean plastic waste on site. We already got 5 LOIs from companies on waste management food companies. We are also collaborating with Osaka University, and also we are doing R&D in the UK. We have offices in Japan, Luxembourg, and the UK. We won several awards, such as from University of Cambridge, Prostor Forum of Solar Impulse Foundation, as well as so many more. So we are looking for technological collaborations in Australia, as well as, of course, for proof of concept and pilot testing, as well as a Series A funding or pre-Series A funding for the next year to expand our test as well as commercialization. Of course, we want to manufacture locally in Australia for the machines and the chemical catalysts once we get these partners. So once again, we want to contribute this problem, especially in Great Barrier Reef and in entire Australia. Thank you for listening, and we are happy to answer your questions.
To the second, well done. You might start down the front this time. Paul?
Great presentation, guys. Really well done, and a really great solution, and he really thought through everything pretty well. My questions are just around just some incremental bits and pieces. Firstly, the carbon that's produced, the end result of the process. You sort of just skipped over what sort of uses that can be put to. Would you mind just giving me a bit more detail about how that then is re-entered back into the economy?
Absolutely.
So the carbon,
Thank you for that question, Paul. Actually, Tadashi, please go ahead, and I'll add onwards.
Okay, so the carbon generated can be used for biofuels or materials of bioplastics activated carbon. So because carbon is a commodity product in the market, so chemical traders or chemical companies can buy. In case of Japan, for example, there are sort of buyers who can buy back from food companies as commodity products.
So how does the cost of that end result compare to, say, carbon from other sources? Is it something that you on-sell, or is it something you give away, or how do you sort of how do you turn that into a revenue stream?
Yeah.
So clients can sell the carbon typically from 5 cents US cents up to 20 cents per kilogram of the carbon from waste.
Mm-hmm. There is one aspect of it we want to highlight, that if you compare it to traditionally sourced carbon, this may be a little bit more expensive. So are bioplastics. What we are trying to highlight is that this is green carbon generated from waste. And this is also how it will appear in the market. That companies who want to reduce their carbon footprint, they're going to look for alternatives, and they're going to find our carbon the solution to their green agenda problems.
Thank you.
I might just ask a quick question just to confirm around your business model. I think what I'm taking is that you are developing a machine